There's a problem in the text that says, show that the square of an odd integer is of the form 8k plus 1. I thought that this was worthy of a video very simply because the procedure that they use to do this is something that will come up again and again. So what we're going to do is we're going to say we have some integer. So we have n is an integer, and I'm going to say any integer. And we are going to take this integer and we are going to divide by 4. So what that means is that there are 4 different ways to actually write down what n is equal to. So we could say n is equal to, it's going to be 4 times some quotient for all 4 of these, but it could be that when you divide by 4 you get a remainder of 0. Or it could be that n equals 4 times the quotient you get, and then there's a remainder of 1. It could be n equals 4 times the quotient with a remainder of 2, or n equals 4 times the quotient with a remainder of 3. The next one would be with a remainder of 4, but that's just like saying 4 goes into it evenly with a remainder of 0 again. So these are your only 4 options for any integer. Now if we are dividing by 3, it would be 3 times the quotient plus 0, 3 times the quotient plus 1, and 3 times the quotient plus 2, and then you would be done. So this is the representative of n, and it has to be one of these 4 things. Now it says we are working with an odd integer. If you have a remainder of 0 when you divide by 4, this one is even. If you look at this we know is even. It's a 2 times 2q. So it's even. It is 2 times some number. If you look at this one right here where your remainder is 2, I could say that that is 2 times 2q plus 1. 2 goes into it evenly, so this is also even. Now notice this has to be an integer. Q is an integer, we're multiplying it by 2, and we're adding 1, so anything that looks like this will also be an integer. These are both even. So that means we only have to look at 2 cases. When n is written as 4q plus 1, or when n is written as 4q plus 3. So what we're going to do is actually square them. It says the square of an odd integer. So I'm going to take 4q plus 1 first. 4q plus 1, and I'm going to square it. So remember to FOIL, you're actually multiplying 2 binomials out. So this would be 16q squared. Your middle term will be a 4q times 1 plus another 4q times 1, so plus 8q. And your last term will be a plus 1. I'm looking for something in the form of 8k plus 1, so I'm going to pull out an 8, factor it out. So I'm going to say that there's an 8 on the outside. It's pretty easy right here for 16q squared. I'm going to say that is 8 times 2q squared. Plus, I pull out an 8 here and I'm left with 1q. I can't pull out an 8 here off of the 1, and that's okay. I'm going to close my parentheses and say plus 1. So k will be this right here. 2 times q squared plus q, which is an integer. We're squaring, we're multiplying, and we're adding. We're not doing any division. Q is an integer, so 2q squared plus q is an integer. So if we start with 4q plus 1 and we square it, we actually do get something in the form of 8 times some integer plus 1. The second one we have to look at is 4q plus 3. So we have 4q plus 3 squared. When we FOIL that or multiply it, we have 16q squared. Our middle term will be 12q doubled, so plus 24q, plus our last term, 3 squared, is 9. So again, I'm going to pull out the 8. So I have 8 on the outside. I'm factoring it out. I'm left with a 2q squared, plus 8 goes into 24 3 times, so 3q. 8 goes into 9 1 time. But that is just 8 times 1 is 8. I still have 1 left over. I can put the 1 on the outside. And you can distribute, add your 1, and you'll see you get exactly this expression here. So in this case, our k would be 2q squared plus 3q plus 1, which is also an integer. So we have it in the form of 8 times some integer k plus 1. And that proof is shown. Okay, now it's interesting to actually look at some numbers with this. So if we take some odd integers, so let's take 3, and we square it. 3 squared is 9, which is can be written as 8 times 1 plus 1. So our k would be 1 in this case. If I take the number 5, an odd integer 5, and I square it, I get 25. That would be 8 times 3 plus 1. It's a different k, but it's still 8 times some integer plus 1. If I take anything, if I take 9, an odd integer, and I square it, I get 81. And that is clearly 8 times 10 plus 1. These three do not prove it. They are just a demonstration of the actual property. This would be a numerical example. Going through the steps up here with a written explanation would be what you would use to actually prove it.